All right, in fluid dynamics, we are talking about moving fluids, and I want to begin with the idea of ideal flow. So with ideal flow, we've got no friction and an incompressible fluid. That means the fluid doesn't expand or compress. And inviscid means there's no viscosity, there's no friction forces inside the fluid. So that's called ideal flow, and there are two equations that we're going to deal with ideal flow. The first one is this equation that says the fluid is incompressible. So what that says is that the total amount of volume passing through the pipe at one point in the pipe is equal to the total amount of volume passing through the pipe at another point. The other equation we're going to use is a version of conservation of energy, because there's no friction, and that says that the pressure at point 1 plus rho GH at point 1 plus 1/2 rho V1 squared should equal pressure 2 plus rho GH2 plus 1/2 rho V2 squared. And that is an equation that basically says the total energy at one point in the pipe should equal the total energy at another point in the pipe. So here's the example problem I want to look at. We've got fluid flowing into the top of a pipe. It goes downhill and then comes out the bottom of the pipe. So water comes out of the bottom of the pipe moving 8.4 meters per second. The pipe has a diameter of 3.0 centimeters at the bottom and 6.0 centimeters at the top. What is the velocity of the water at the top? What is the pressure difference from the top to the bottom? And if the water exiting the pipe at the bottom is at atmospheric pressure, what's the pressure at the top? Okay, so to solve this, we're going to be applying the two equations that I mentioned above. And to get part A, we're going to be using the velocity equation. So the velocity equation, or the continuity equation. So for part A, we're going to say that the velocity at the top times the cross-sectional area at the top should equal the velocity at the bottom times the cross-sectional area at the bottom. Okay, so these are circular pipes, so the velocity at the top times pi r at the top squared is equal to the velocity at the bottom times pi r squared at the bottom. I'm sure you guys hear my two puppies playing in the background. They are having fun playing with each other, and I'm the only one at home, so I cannot send them away. So we just get to listen to them play. All right, so I'm going to solve this for the velocity at the top. The velocity at the top is equal to the velocity at the bottom times pi r bottom squared divided by pi r top squared. We can cancel the pi's. The velocity at the bottom was 8.4 meters per second. 8.4 meters per second. And the radius at the bottom is 1.5 centimeters, which is 0.015 meters squared, divided by the radius at the top, which is 3 centimeters, which is 0.03 meters squared. And so that equals 2.1 meters per second at the top. So, does it make sense that it slowed down? It was going 8.4 meters per second at the bottom, and now it's going 2.1 meters per second at the top. Is that reasonable? Sure, because when the pipe gets smaller, the velocity has to get faster, so it should be moving slow at the top. Okay, so for part B, we want to find the pressure difference. So to find the pressure difference, we're going to use Bernoulli's equation. It says the pressure at the top plus 1/2 density velocity at the top squared plus rho g h at the top is equal to the pressure at the bottom plus 1/2 rho velocity at the bottom squared plus rho g h at the bottom. And so what I'm going to do to find the change in pressure is we'll do pressure top minus pressure bottom. So I'll subtract pressure bottom from both sides, and that's going to give me delta P okay, plus 1/2 times 1,000 is 500 times velocity at the top, 2.1 squared, plus 9.81 times 1,000 is 9810 times the height at the top, and the height at the top is 2 meters. That was given in the problem. That was given over here in the picture. Maybe you can't see it. That's in blue right there. 2 meters. So the height at the bottom is 0. All right, and that is equal to, we've already subtracted pressure on the bottom to get delta pressure. So we have 1/2 rho, that's 500. Oh, the density of water is 1,000. So I'm plugging in 1,000 kilograms per meter cubed for water. Velocity at the bottom squared, so that is 8.4 squared. Plus 0, because the height at the bottom is 0. So the difference in pressure, that is the pressure at the top minus the pressure at the bottom, is equal to 500 times 8.4 squared minus 2 times 9810 minus 500 times 2.1 squared is equal to 13,455 pascals. Okay, so the pressure difference is 13,455, and the top is at higher pressure because we did top minus bottom, and we got a positive answer. Okay, and then part C says, great, if the pressure at the bottom is equal to atmospheric pressure, what's the pressure at the top? Well, atmospheric pressure is 101,300 pascals. So the pressure at the top is 13,455 more than that. Oops. 13,455 plus 101,300. So we get the pressure at the top is equal to 1114,755 pascals. Now, we do want to get the correct number of significant digits. There are 2 significant digits in this problem. So for part B, delta P would be 13 kilopascals, or 13,000 pascals. And here, for part C, the pressure at the top is going to be 110 kilopascals. Rounding that to 2 significant digits, you just get 110. And I'm putting it in kilopascals. You don't have to. You could write this as you could write this as 1.1 times 10 to the times 10 to the 5th pascals. That would be a perfectly good way of writing it with 2 significant digits. Probably the best way to write it with 2 significant digits. All right,